Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, glad to be here with you today. I'm Husnul, co-author of this paper. The paper title is Ship Heading Control Using Nonlinear Model Predictive Control. I represent the other authors, Mrs. Tahiyatul Asfihani, Mrs. Irma Fitria, and Mr. Subhan. Well, now let's get started. Okay, in this moment, these are the points that we want to share with you. We will start with an autopilot system. An autopilot system drives the ship automatically without manpower, and the ship motion uses the ship's rudder for changing the ship direction. A good maneuver requires a proper hydrodynamics interaction between the control and the ship's structure as a whole. The ship heading control is provided to control the motion of a ship at sea. A design of the ship heading control uses a various method. There are control methods based on mathematical models or not. And the ship motion can be represented by a mathematical model, either linear or nonlinear. Model predictive control or MPC is one of the control methods based on a mathematical model of a system. MPC is applied for a discrete linear system. MPC has a step to predict an output system for improving the input control so an output system can reach the target more accurately. Moreover, MPC can handle constraints, multi-input, and/or multi-output. These advantages have made MPC used in many fields, such as in ship heading control, missile control, control of an autopilot car, etc. Based on previous research by Asfihani et al., which is about a ship heading control for following the Dubin's path, MPC for the ship heading control has good performance. The development of MPC for a discrete nonlinear system is Nonlinear Model Predictive Control or an MPC. Ability of an MPC for trajectory tracking and collision avoidance was discussed. An MPC can force ships to avoid collisions with static or dynamic objects affected of system disturbances. Furthermore, an MPC was used for a ship dynamic positioning system, and it is effective and satisfied. In this paper, the mathematical model of the ship motion is nonlinear. The motion of the ship is considered to be 3 degrees of freedom, namely sway, yaw, and roll. This research assumes that the surge velocity is constant. Well, the ship heading control was designed using an MPC by considering some constraints. The constraints are both state and control. Now we go to the second part. As known, the movement of the ship has 6 degrees of freedom. For a ship heading control, the influential motions are surge, sway, yaw, and roll. Because of the assumption, surge velocity is constant. So the ship motion considered is 3DOF. In an MPC, the mathematical model used is a discrete nonlinear system. So the previous equations are changed in a discrete model using fourth order of Runge-Kutta with time sampling h. And after this, we substitute the variable with the parameters to the equations. In this part, we will design the control. The objective of ship heading control is to achieve desired ship heading angle by optimizing the rudder angle, so that the error of ship heading angle and desired heading angle is minimum. The objective function of the ship heading control is given as follows. Next, the constraint function. The output system are yaw angle and yaw rate. The constraints are two types, included the constraints on the input control and the constraints on the state variable. These constraints can be described as follows. The algorithm in this design of the ship's heading control with an MPC is carried out as in the steps below. First, specifies initialization value of the state variable. Second, perform the NMPC optimization process. Third, the first input control resulting from optimization is applied to the system model. Fourth, for the iteration k plus 1 repeat from step 2, simulation is used to determine the performance of system by the given optimal control. The initial value of sway, yaw, and roll angle are 0, 30, 0 degrees respectively. The wake matrices Q and R are constant at each time. The total time of simulation is 100 seconds. The lower bound of yaw rate is minus 0.0932 radian per second, and the upper bound of yaw rate is 0.0932 radians per second. The lower bound of the rudder angle is minus 35 degrees, and the upper bound of the rudder angle is 35 degrees. The first simulation varied the values of time sampling H for discrete process in Runge-Kutta. The variational values of time sampling are 0.5, 0.8, and 0.9. The first simulation result shows that the best value of time sampling is 0.5. The results shown in the table and figure that displayed. In this table, the best sampling time is 0.5 because the value make the output system reach the reference fastest. The second simulation applies some values of the prediction horizon in NMPC by time sampling H 0.5. The figures show that the number of prediction horizon affects the time to reach the reference. The variational numbers of prediction horizon are 10, 15, and 20. The simulation results show that the time to reach the reference is 10, 15, 20 are 8.3, 5.3, and 3.9 respectively. The prediction horizon 20 has better performance. Furthermore, the first simulation and the second simulation are used to determine the best conditions for the ship heading control. The third simulation runs the best conditions obtained. The third simulation shows on the figures that the yaw rate is within the bound. Well, the design of ship heading control using NMPC was discussed. The ship heading control is obtained based on the mathematical model. The ship motion is presented by 3 degrees of freedom model: sway, yaw, and roll. The input system is rudder angle, and the output system are yaw angle and yaw rate. The ship heading angle is observed by yaw angle. The best condition for the simulation is determined based on the value of time sampling and the number of prediction horizon. The simulation results show that the ability of NMPC to drive the ship to follow the desired heading angle and constraints can handle. Well, thank you so much for your attention. Assalamualaikum warahmatullahi wabarakatuh.